Hello everyone, welcome to this fourth video on complex integration. We are going to see the second set of problems like application of Cauchy residue theorem to evaluate real integrals. In the last session we saw about what is meant by Cauchy residue theorem and how to evaluate the value of integrals using Cauchy residue theorem. Now we are using the same Cauchy residue theorem to evaluate real integrals of certain predefined types. So we will see how to apply them. What we know about Cauchy residue theorem, you will try to recollect. Integral over C f of z dz is 2 pi I times summation of the residue of f of z at the pole z1, z2, z3 up to zn. So you find the residue of the function at various poles, add them up and then multiply with 2 pi I. So this is what your Cauchy residue theorem says. Now about estimation of residues. At the simple pole, that is if power is going to be equal to 1, then the residue is given by limit z tending to a, z minus a into f of z. And at multiple pole of z is equal to a of order n, then we have the residue to be limit z tending to a 1 by n minus 1 factorial d power n minus 1 by dz power n minus 1 the derivative z minus a power n times the order into the function f of z. Now keeping these things which was primarily and was already covered in our last video, we will try to see how we can apply the Cauchy residue theorem to evaluate real integrals. The type 1 problem which we are going to cover is where we are going to integrate around a unit circle, and the integration is going to be of a predefined type of the format integral from 0 to 2 pi a function of cos theta sin theta d theta, where function of cos theta sin theta d theta is going to be a rational function in terms of sine and cos. What we know about the complex number z, I know that I can express complex number z as r e power I theta. But what we find or use over here is unit circle. What do we mean by unit circle? Circle of radius to be equal to 1 units. If I have radius to be equal to 1 unit, what will happen to my complex number z? R will be replaced as 1. So I will be having this z to be equal to e power I theta, which is cos theta plus I sin theta. So what will be the conjugate of the complex number z? It will be z inverse, which is e power minus I theta. So this plus sign over here gets replaced with a minus sign over here, and we have this as cos theta minus I sin theta. Now look into the primary target. What is the target? I will have to evaluate the integral from 0 to 2 pi, a function of cos, sine and theta. This is a function of cos, sine, theta, which we are now going to convert it in terms of my complex number called as z. So I know that z is equal to e power I theta, and I know that z inverse, the conjugate, is e power minus I theta. Using these two format, I am going to rewrite my cos theta. How to get my cos theta? E power I theta is going to be cos theta plus I sin theta. E power minus I theta is cos theta minus I sin theta. When I add these two terms, what will happen? Cos and cos, cos will become 2 times of cos, and this plus I sin theta and minus I sin theta will cancel off. So I will have e power I theta plus e power minus I theta to be equal to 2 cos theta. So this gives me cos theta is e power I theta plus e power minus I theta divided by 2. In a similar fashion, when I want to extract the sin theta, how to get your sin theta? Instead of adding them, you subtract the quantity. So when we subtract, cos and cos will get cancelled off. I and minus of minus I will become plus I. So I will have 2i sin theta. So 2i sin theta will be e theta minus I sin theta minus e power I theta. So sin theta can be written as cross multiplying e power I theta. We subtracted it. So e power minus I theta divided by, what was the divisor? You had 2 times of I. You will have to be careful about this I. So when I want to convert this function in terms of cos and sine into a function of z, then I will go for substitution, which is now aided by cos theta is z plus z inverse divided by 2 as we had over here, because what we know about e power I theta? E power I theta can be represented as z. And what is this e power minus I theta? It is nothing but z inverse divided by 2. So how I can write cos theta as? I can write my cos theta as z plus z inverse divided by 2. So when I replace the z plus z inverse, so 1 by z divided by 2. So z can be cross multiplied. Z square plus 1 is the LCM, and the z comes down with 2z. So what is my replacement for cos theta? My replacement for cos theta is z square plus 1 divided by 2z. In a similar fashion, I can replace this sin theta as z minus z inverse divided by 2 times of I. Z minus z inverse divided by 2 times of I. Similarly, you bring this 1 by z to the denominator divided by 2i. Z on cross multiplication gives you z square minus 1 divided by 2i. This LCM of z comes down. So sin theta is replaced as z square minus 1 by 2i z. So in my integral, wherever I have cos theta, I will replace it with z square plus 1 by 2z, and wherever I have sin theta, I will replace it with z square minus 1 by 2i z. The third part which has been left out for me is the d theta part. I have replaced cos, I have given a replacement for sin, I will have to give a replacement for d theta in terms of z. How to do it? Z is e power I theta, differentiate on both sides, dz will be equal to e power I theta on differentiation is e power I theta into I times d theta, because the constant over here is I. So it is going to be written as I, e power I theta can be rewritten as z into d theta. So keeping here d theta to the left hand side, the remaining things can be cross multiplied. So we have d theta to be equal to dz divided by iz. So I need to remember 3 substitution formula for my type 1 problem, which is evaluated for a unit circle. This point is very, very important, because what is going to be our boundary? The boundary is mod z is equal to 1. A circle with center 0, 0 and radius to be equal to 1 unit. So this is going to be our boundary, where I am going to replace cos theta by z square plus 1 by 2z, sin theta by z square minus 1 by 2iz, and d theta by dz divided by iz. So keeping all these things in mind, plus the Cauchy residue theorem, we will now move on to evaluate the integral 0 to 2 pi d theta divided by 5 plus 3 cos theta. So this integral, which is going to be from 0 to 2 pi, a function of, you don't have a cos over here, just a sin theta, cos over sin over here, we just have a function of cos theta. So I will have to say what is going to be the substitution for my cos theta, say what is the substitution for my d theta, and in which case after resubstituting all this quantity, the problem will get converted to z. So come on, say what is going to be the conversion for cos theta. We know that the conversion for cos theta is z square plus 1 divided by 2z, and d theta is replaced as dz divided by iz. I now put everything back in my integration, so that this integral, which was from 0 to 2 pi, will now become integral along the closed curve C. And what is my closed curve C? The unit circle mod z is equal to 1. So first my limit 0 to 2 pi gets converted. Next d theta gets converted as dz divided by iz. And now 5 plus 3 times cos theta gets converted as z square plus 1 divided by 2z. So now let us take the LCM, integral over C, dz divided by iz. So 5 into 2, that makes it as 10z plus 3z square plus 3 divided by the total LCM is 2z. Ez can be cancelled off. So this leaves me with integral over C. This 2 goes to the numerator. So 2 divided by I dz divided by 10z plus 3z square plus 3. Now let me rearrange this quantity in order of z. So this can be rewritten as highest power 3z square plus 10z plus 3. Now let me make this z to be of unit coefficient. How can I make it as unit coefficient? By pulling out a 3 outside. So I have dz divided by z square 10 by 3 times of z plus 1. So now I have in my denominator a function of z valid for z square plus 10z by 3 plus 1 with a constant 2 by 3i in the front. Now I will be using my Cauchy residue theorem to find the value of this integral. Now we will quickly recollect the steps for Cauchy residue theorem. The first step is to find the pole. The second step is to define your boundary. The third step is to find the check or the position of the poles, whether they lie inside or outside the boundary, and according they are simple or multiple pole, evaluate the residue, add your residue, multiply by 2 pi I. This is going to be a quick recap on the Cauchy residue theorem's evaluation. So now we will try to proceed them one by one. So the first thing which we need to do now is going to be estimation of poles. How to get your poles? Equate your denominator to 0. So what was my denominator? Denominator was z square plus 10 by 3 times of z plus 1 equal to 0. So let me use the formula. Z is equal to minus b plus or minus b square minus 4ac the whole root divided by 2a, since z is going to be a quadratic equation. So I have this to be equal to my a, this to be equal to my b, this to be equal to my c. Hence I have minus b, so minus 10 by 3 plus or minus 10 by 3 the whole square minus 4 into 1 into 1 the whole square root divided by 2 into 1. So that minus 10 by 3 plus or minus 100 divided by 3 square is 9 minus 4 the whole square root divided by 2. So let me take the LCM. Minus 10 plus or minus 100 minus 9 4s are 36 the whole square root divided by 3 over here, and square root of 9 will be 3 over here. So 3 comes to the denominator, and already there is a 2 in the denominator. Minus 10 plus or minus root over 64 divided by 3 2s are 6. What do we know about 64 square root? It is 8 divided by 6. So I have this as minus 10 minus 8 divided by 6, or it is minus 10 plus 8 divided by 6. Hence we have the poles to be equal to minus 18 divided by 6. So that makes it as minus 3, or it is going to be minus 2. This is going to be minus 18 by 6, or we have this to be equal to minus 2 by 6, in which case it is minus 1 by 3. So my poles are being estimated in my step 1 as minus 3 and minus 1 by 3. In which case what I can do is I can replace z square plus 10 by 3 times of z plus 1 in the format z plus 1 by 3 z plus 3. This is how I can rewrite this expression in terms of the pole as. So I now have the integral over c 2 divided by 3i dz divided by z plus 1 by 3 z plus 3 with my poles to be equal to minus 3 or minus 1 by 3. Now my second step. What is my second step? To identify the boundary. What is my boundary? We are integrating along a unit circle. What do we mean by unit circle? Mod z is equal to 1. X plus iy equal to 1. X square plus y square the whole root equal to 1. X square plus y square equal to 1 square. It represents a circle with center 0, 0 and radius to be equal to 1 unit. The next thing is to plot your boundary. Here we have the unit circle with center to be equal to 0, 0 and radius to be equal to 1 unit over here. So this is going to be our radius 1 unit. Now the position of the poles over here, the poles are going to be z is equal to minus 1 by 3, z is equal to minus 3. These are going to be my two poles. Let me introduce an I0 over here so that in my x and y coordinate I can write this as minus 1 by 3 comma 0, and in my x and y coordinate I can write this as minus 3 comma 0. Let me now plot the poles over here in this graph. Minus 1 by 3, 0, minus 1, minus 1 by 3 will be over here inside. So this pole z is equal to minus 1 by 3 lies inside the modulus of the circle. Now moving on to the second pole, z is equal to minus 3. Where is going to be minus 3 comma 0? One second. The point minus 1 by 3, I am sorry, it is over here in your x-axis. So where will be the point minus 1 by 3 comma 0? Over here. This will be my point minus 1 by 3 comma 0. Sorry for the mistake. And now with this lies inside the unit circle, mod z is equal to 1. Now coming for the second circle, which is going to be minus 3 comma 0. In x-axis minus 3. Where is my minus 3? This is going to be over here, minus 3 comma 0. So what do we say about the second pole minus 3 comma 0? It lies outside the unit circle. So only one of the poles is going to lie inside for me, and the second pole is going to lie outside for me. So for the pole that lies outside, always the residue turns out to be equal to 0, and we will have to now estimate only the residue for the pole that lie inside, which is going to be given by minus 1 by 3. So this completes my step 3, identifying the position of the poles. Now moving on to your step 4. What is your step 4? Find the residue at the poles. Residue at the poles. What is going to be my pole? My pole is going to be z is equal to minus 1 by 3. So we will quickly try to copy paste the formula for our residue. The value of the residue is given by limit z tending to a z minus a into f of z. So what is my function first? I need to identify my function f of z. My function f of z is going to be equal to, what is going to be here? 2 by 3i 1 divided by z plus 1 by 3 z plus 3 z plus 1 by 3 z plus 3. So this is going to be my function f of z. Now applying the limit at the pole, limit z tending to minus 1 by 3 z minus of minus plus 1 by 3 into my function f of z. So it is z plus 1 by 3 into the function 2 divided by 3i 1 divided by z plus 1 by 3 into z plus 3. So plus 3 and plus 1 by 3 can be cancelled off. Now we can apply limit z tending to minus 1 by 3 in the given quantity. So when we move on to apply it, we have the value to be equal to limit z tending to minus 1 by 3 2 divided by 3i. The remaining quantity is 1 divided by z plus 3. So 2 divided by 3i. Let me replace this z with minus 1 by 3 plus 3. So this makes it as 2 divided by 3i minus 1 plus, take the LCM, 3 3s are 9. This 3 goes to the numerator. So I have this 3 to be cancelled off over here. 2 divided by 9 minus 1 makes it as 8i. So this is going to be my residue at the pole z is equal to minus 1 by 3. What do I know about the residue at z is equal to minus 3? Since it is going to be outside, the value of it is going to be equal to 0. Now considering the Cauchy residue theorem, integral over c f of z dz is 2 pi I times the summation of residues of the function f of z. So it is 2 pi I times, the first residue was 2 by 8 times of I plus the second residue was 0. Ignoring it, we have this I to cancel off over here, 2 2s are 4, can be cancelled off over here, 2 times it will remain. So the final answer for the integral 0 to 2 pi d theta divided by 5 plus 3 cos theta happens to be pi by 2, and what we have used the Cauchy residue theorem to evaluate this integral. So quickly have a recap. Replace the d theta by dz by iz, since we have a cos function, replace it by z square plus 1 by 2z. Then follow the substitution method. This will be getting converted to a function of z. When I convert it into a function of z, now I can apply the Cauchy residue theorem. The first step is to find the poles. The second step is to identify the boundary. The next, plot the poles in the boundary and see whether they lie inside or outside. And the last step is to estimate the value of the residue and then substitute them in the formula 2 pi I times sum of the residue. So this completes the problem on evaluation of a real integral using Cauchy residue theorem. Thank you.